Hello everyone, welcome back to my YouTube channel. So now we are going to solve question number 2 of weekly contest 458. Before starting, if you guys haven't subscribed my YouTube channel yet, then please go ahead and subscribe it. Now without any delay, let's get started with this problem. Minimize maximum component cost. Okay, so let's read the problem statement now. You are given an undirected connected graph with n nodes labeled from 0 to n minus 1 and a 2D integer array edges where edges of I is equal to u, v and w denotes an undirected edge between node u and node v with weight w and an integer k. Okay, you are allowed to remove any number of edges from the graph such that the resulting graph has at most k connected components. Okay, so here let's suppose this is one node A, B, C, okay, and this is D. All right, so now this is nothing but a connected graph, right? All the nodes are connected with each other. Now if I remove this, okay, remove this edge, so now if you see, this is one graph and this is one more graph. Okay, right? So total two components are there. Okay, so here see, this node is not attached to any other node. Okay, and all these three nodes are connected to each other, right? C connected with B, B connected to A. Okay, so I can move from one node to any other node, right? But here if I just remove the connection between C and D, so from D I can't move to any other node, right? So here that's simply two components. Okay, so that's the meaning. So the cost of a component is defined as the maximum edge weight in that component. Okay, maximum edge weight. So A to B, let's say weight is 10 and B to C weight is 20. So in this component the maximum edge weight is 20, right? So I will take that. The cost of a component is defined as the maximum edge weight in that component. If a component has no edges, here see this D, no edges, so its cost I'm going to take 0. Okay, so we have to return the minimum possible value, okay, of the maximum cost among all the components after such removals. Okay, so we have to make sure that we get the minimum possible value only, okay, of the maximum cost among all the components. Okay, so here let's suppose what it is saying, let's suppose this is 60. Okay, now this is one complete component. Okay, all the nodes are connected, so cost is 60, right? We want the minimum, we want the minimum possible value. So when I'm going to get the minimum possible value, let's say k is 2, so that simply means I can have two components. So when I'm going to get the minimum possible value, when I'm going to delete the weight with the max value, right, 60. Okay, so this is the only possible scenario. So let's say I remove this 60. Now I have two components again. So now if you see here in these two components, max weight is going to be 20 now. Okay, okay, so minimum possible value of the maximum cost, right? So very simple, right? So now see this example number 1, n is equal to 5. So initially if you see the constants, okay, of this problem, you will find out that initially all the values are connected, all the nodes are connected. Okay, so there is only one single graph initially, right? So here 0 to 1 weight is 4. Okay, so this is unconnected graph, right? 0 to 1 there is, and simply means 1 to 0 also there is one edge. Okay, so 0 to 1 weight is 4, 1 to 2 weight is 3, 1 to 3 weight is 2, okay, and 3 to 4 weight is 6. Okay, k is equal to 2. Okay, so two components we can create. So right now this is just one component. Okay, so two components we create. Okay, so what we need minimum possible value. So definitely I'm going to delete this max weight. Okay, so I will remove this. Okay, now if I remove this, I will have two components, 1 and 2. Okay, so now among them the max, okay, I need to return the max. Okay, so here 0, 4. Okay, so among them the max is 4, so I have to return that. 4 is coming because this is a max weight in this component. 0 because it's not connected anywhere, so we have to take 0. Okay, so among them max, and we have to make sure minimum first. Okay, that's it, very easy, right? Okay, remove the edge between nodes 3 and 4, weight is equal to 6. The resulting component have costs of 0 and 4, so the overall maximum cost is 4. That's it. Okay, so how we are going to solve this problem, right? So here if you see, we are talking about components. Okay, So whenever in the graph problem you see such a word, okay, components and all that, so that simply means we are talking about DSU, okay, or find union, okay, find union. So here what I'm going to do, let's understand with this example, okay, this is very good example, okay. So let me show you with this, okay. So here if you see n is equal to 3, that simply means that we have nodes 0, 1 and 2, okay. That's the simple meaning of this, right? So here 0 to n minus 1, right? 0 to 2, okay. Okay, cool. Now here if you see, initially what I'm going to do here, I'm going to create one parent array, okay. Let's suppose this is my parent array, 0, 1 and 2, okay. So I will say that parent of 0 is 0 only, parent of 1 is 1 only, and parent of 2 is 2 only, okay, right now initially. So I am making every node has its own parent, okay. Right now I'm not iterating over edges, okay. Now here these are the components, right? So here if you see this is one component, okay, this is one component. So let's suppose A, B, C and D, okay. So A is connected with B, B is connected with C, C is connected with D, and let's suppose A is also connected with D, okay. So here let's suppose weight is 10, 20, 30, 40, okay. So now if you see, this is just one component, right? All are connected, right? From any one node I can go to any other node, right? Okay, so in this component what is the max weight you are going to get? You are going to get 40, okay. But there is one more possibility now, right? Even if I disconnect this edge, okay, from A to D, it is still one component only, right? Again, from any one node I can go to any other node, from D I can go to A, okay. Still it's still one component only. So now what is the max bit I'm going to get? 30. So here, from here what I conclude, that uh like this A to D and C to D, okay. So I will remove extra edge, okay. If it is already part of component, then I don't need to take that, okay. So because if I take that, I will get to the max 40, okay. I don't want that, okay. We need the minimum possible value also, right? So here, from here I conclude that 10, 20 and 30, okay. With just these three weights I'm still able to move from any one node to any other node. It's still just one component, so I don't need to connect from A to D because it will increase the value to 40, okay. That's the simple meaning, okay, what I'm saying. So from here I conclude that let's sort our edges depends on these weights, okay, depending on these weights. So what I'm going to do here, 0 to 2, first I'm going to write this 0 to 2 weight is 6, okay. Sorting them based on weight, 6. After 6, 80 comes or 46? 46 comes. So write this 1, 2 and 46, done. Then after 46 what comes? 80, okay. So write this 0, 1 and 80, okay, done. All right, so now this is nothing but my sorted edges, okay, sorted edges. All right, so now here let's solve this first, this part, okay. 0 to 2, 6, okay. So weight is 6, all right. And 0 to 2, 0 to 2, and here k is equal to 1, only one component we need, only one component, okay. So here 0's parent, okay. So here 0's parent is 0 and 2's parent is 2, okay. So both are having different parents, right? So what I'm going to do, I'm going to do the union among them, okay, union among them. So I'm going to say a0, let's take 2 as the common parent, okay, done. So now 2's parent is also 2 and 0's parent is also 2, okay. This is what I'm going to do, I merge them, okay. So initially 0 is here, 2 is here, right? Now I'm joining them, okay, joining them. So now in this I'm saying that let's take this as the parent only, this as the parent. So 0's parent is also 2 and 2's parent is also 2, okay, since I joined these two, right? 0 to 2 there is an edge, okay. 0 to 2 there is an edge, right? So I'm going to say let's take this as parent. So parent of u I'm setting it to 2, okay. So here I'm just going to update it to 2, that's it. So if both are having different parents. Okay, then I'm doing the join among them, and then I am adding the weight here. Okay, this weight 6. Okay, first I see whether these two are different. Okay, having different parents, so I'm going to combine them. Okay, so after combining I will add this weight here 6. All right, this is done. Now after that, here this is done. Now here 1 to 2 and 46, one's parent is 1, two's parent is 2. Okay, now both are different, right? So I'm going to do here, I'm going to join them. Okay, 1 and 2. Okay, both are having different parents, so let's add this weight here also, 46. Now here I added this. Okay, so one's parent is 1, two's parent is 2. Okay, so here again parent of 1 I'm making it 2. Okay, since I'm joining, so this is done. All right. Okay, now here if to see 0 1 0 to 1, here also change it to 2 now. Last time 1 to 2 I changed to 2. Okay, now after this if you see 0 to 1 80, zero's parent and 1 parent both is 2. Okay, we don't need to connect 0 and 1, right? We don't need to connect this because it's still one component only, right? We don't need to connect this. Okay, it's still one component. Now if you see in this the weights where we have added these weights, so among that which value is max? So max is 46, so our output is going to be 46 for this one, not 80. Okay, so while running the code you can add this test case and run it. Okay, you will get the output as 46. Okay, so this is what we need to do, right? Okay, so this is one thing. Okay, so in this case I have explained why we don't need this. Okay, because we still if even if I join this now, it's still one component. Even if I don't join, it's still just one component. But if I join this now, I will get output as 80. That is not wrong. We need output as 46 only. Okay, so that's the reason. Done. Now here in this case also you have to sort them based on increasing order. So first you are going to write this 1 comma 3 comma 2. Then after that you are going to write this 1 2 comma 3. Then you are going to write this 0 comma 1 comma 4, and then you are going to write this 3 4 6. Okay, 3 4 6. All right, so in this case 1 and 3 both are having different parent. Okay, so 0 to first 0 to 4. Okay, 0 1 2 3 4. Okay, all are having same parent. Okay, 0 parent 0, 1 parent 1, 2 parent 2, 3 parent 3, 4 parent 4. Okay, so now here if you see this case 1 2 3 both are having different parents, so I'm going to make the one parent as 3 only. Okay, and I'm going to add this. Okay, so weight 2. Okay, I have added this weight 2. Then 1 to 2. Okay, 1 and 2 both are having different parent. Okay, so here I'm going to make the one parent 2 only. Okay, so let's say I make this 2. Okay, and I will add this. Okay, so 1 2, and here this is nothing but 3, right? So add this 3. Okay, done. Now here after this 0 1. Okay, 0 and 1 both are having different parents, so here I'm going to make it 2, and I'm going to add this. Okay, done. Now 3 and 4 parent is different. Okay, 3 three's parent is uh three's parent is here this part I'm solving, right? So three's parent is nothing but 3, and fourth parent is nothing but 4 only initially, so I'm going to make this same thing. Okay, so 3 3. Okay, different, so I'm adding this weight. Okay, I have added this, right? So now this is done. Now this is done. Okay, I get this. I have added all the weights in this 2 3 4 6. Okay, done. Okay, so now here k is equal to 2. That simply means uh, k is equal to 2 means we can have two components. Okay, right? So for getting the two components we have to remove one edge. Okay, so k minus one number of edges we need to remove, right? So I'm going to remove the last value. What is the last value? Okay, from here. So what is the now what is the max from here? Max is 4, so that is my output. That's it. Okay, so now you can try to solve this problem by your own. Okay, you can write the code. Now I'm moving to the coding part. Okay, so here this is the solution for this. Okay, so first we have to sort the edges. Okay, so based on their weight. Okay, in the ascending order. Then we have to initialize the union find. So parent we are taking, and I'm assigning like 0's parent as 0 only, 1's parent as 1 only. Okay, so this is what I'm doing here. Then here we have to check the weights. Okay, done. Then we have to build this minimum spanning tree using the Kruskal algorithm. So I'm iterating over all the edges one by one. So we have u v, okay, u to v or v to u, there is one edge, and w is the weight. Okay, so I'm checking the parent of this, okay, and parent of this. If both parents are different, then only then in that case I am adding the weight. Okay, and also I'm doing the union of parent. I'm making the parent of this one to this one. Okay, that's what I'm doing, right? And then I'm recording the weight. Okay, only when, if parent of u is not equal to parent of v. Okay, only then we have to remove the k minus 1 largest weights from the end. Okay, so I told you k components, that simply means k minus 1 number of edges we need to remove. So I'm just going to run one loop, int I is equal to 0, I is less than k minus 1. Okay, and here starting from 0, that's why less than. Okay, and minimum spanning weight is empty. Okay, if it is not empty, then we have to stop, right? I plus plus. So then we have to remove the last one. Okay, remove the largest one. Okay, until then here in the end we have to return the max remaining weight. Okay, or 0 if none left. Okay, so mst weights dot get last size. Okay, what is the max size? So this is how this union find with the path compression works. So find method, so in this we are passing parent array and x value. Okay, so if parent of x is not equal to x, then I'm going to update the parent of x. Again I'm going to call the find, okay, parent and that parent of x. Okay, path compression. So we have solved we have written this code many times, okay, in many problems union find. So this is very common structure, okay, for all the problems, right? So here what we are checking, if one parent is 1, then we are good. Okay, then return. But if parent of 1 is not equal, is something else too, then again we have to call this find. Okay, again we are passing this array, then we have to check the parent of this. Okay, like that. Okay, so this is a solution for this. So I hope that you guys are able to understand this problem, question number 2. If you guys still have any doubts, then please feel free to ask in comment section. Till then, keep coding and keep practicing. Meet you guys in the next video. Thank you. Bye bye.